Welcome to Energy Talks, a regular podcast series with expert discussions on power system testing topics. My name is Scott Williams from the podcast team at OMICRON, and I will be your host. Power transformers are a key element of the electrical grid, and they are continuously subjected to different levels of electrical, thermal, mechanical, and chemical stress during service. To ensure their reliable and safe operation, it is key to assess the condition of the insulation system during a transformer's life cycle. Partial discharge measurements, for example, are a highly effective and non-destructive tool for the detection, assessment, and localization of insulation weak spots, which could eventually lead to transformer failure. In this episode, we are going to focus on the importance of performing on-site partial discharge measurement and analysis on power transformers. With me to discuss this topic is Michael Krüger, one of the original developers of OMICRON's CPC 100 multifunctional electrical testing system, and he is also a longtime asset expert at OMICRON. Michael has over 30 years of experience performing partial discharge measurements on electrical equipment. Hello, Michael. Welcome to Energy Talks.
Hello, Scott. I'm happy to be here and to have the possibility to speak with you about partial discharge measurements.
Super. Great to have you. Also with me is Udo Ranninger. He is a regional OMICRON application specialist with a focus on partial discharge measurement and analysis. Hello, Udo. Thank you for joining us.
Hi, Scott, and thank you for the invitation.
Super. Again, great to have you both here. Michael, you have had over 30 years of experience in partial discharge measurement. Could you give us a brief history about how this measurement was performed earlier?
Yes, Scott. Partial discharge measurement has a very long history. It's not a new technology. I think it was started in the late 50s or beginning of the 60s. And in this time, they didn't call it partial discharge measurement. It was called radio interference voltage measurement. And the test instruments were similar to a shortwave radio.
Yes.
And so it was narrow band, and you could tune the frequency. And first it was applied for measuring the magnetic or the electromagnetic interference coming from corona on the overhead lines. And then they introduced it to test also insulation.
Boy, PD testing has certainly advanced over the years to become the sophisticated diagnostic solution it is today. Michael, could you please briefly explain how partial discharge testing enables us to determine insulation condition in power transformers?
Yes, Scott. There are several aspects in insulation condition assessment. On the one hand, we have integral measurement methods like insulation resistance measurement, tangent delta measurement, or dielectric response measurement. And we can do it in the frequency domain with FDS, that means frequency domain spectroscopy, or we can do it in the time domain with polarization depolarization current, PDC measurement. And with those methods, we can detect general aging of the insulation and, for example, moisture, which is very important, for example, in big power transformers. And on the other hand, we might have partial discharges. And partial discharges are local electrical events or discharges, or we can say arcing in a small area of the insulation. Small PD, partial discharges, cannot be detected by the integral measurements I mentioned, like the insulation resistance. And the local arcing produces, in most cases, first electromagnetic radiation, second, acoustic radiation, which is very important for localization of partial discharges. Then it can produce gases in oil, which can be detected by the dissolved gas analysis. I come to this a little bit later. And it will erode solid material, which makes partial discharge dangerous for solid material, but also for oil-filled equipment.
Okay. So when are partial discharge measurements typically performed on power transformers?
Yeah, then we have also to distinguish between oil-filled power transformers and dry type transformers with cast resin insulation. So for oil-filled power transformers, it's mandatory to make a test in the factory when the voltage level is higher than 72.5 kV according to the IEC standard. On-site PD measurements on oil-filled power transformers are typically performed when you have any indication from some gases which is detected by the dissolved gas analysis. Normally, you don't make PD measurements on transformers as a routine test. So normally we have an indication by the DGA. For dry type transformers, it's totally different. PD testing is the most meaningful test to assess the insulation condition. It's normally performed during the factory acceptance test, so in the factory. And on-site PD tests are coming more and more, and they are requested especially if an outage of such a transformer causes high follow-up costs. Also, insurance companies often request PD testing, maybe annual or every 2 years, to reduce the risk of a big damage.
Okay, interesting. You mentioned the growing trend for on-site partial discharge measurements on power transformers. Why are they so critical?
Yeah, partial discharges can destroy a transformer, especially if the PD, the partial discharges, occur continuously during the normal operation with a nominal voltage. If you have a test voltage which is much higher than the nominal voltage, it might be acceptable. But if it is continuously discharging during the service, during the normal operation, it might be critical. And I already mentioned that partial discharges can erode solid material. And if it is arcing continuously, then it's also eroding continuously. And then it's a question of time that the transformer will fail by an internal breakdown. For oil-filled transformers, it's a little bit different. So they are a bit more resistant against oil.
Yes.
And if you have some bubbles in the oil, they can also recover. And so it's sometimes it's like a self-healing process. And so the gas in oil or dissolved gas analysis is a good tool for detecting PD in oil. But if the PD are located in solid parts, solid insulation parts, or in the bushings, in the high voltage bushings, for example, the DGA cannot show the key gases of PD. In those cases, the PD measurement is the only possibility to detect it.
Okay, interesting. Michael, you and Udo recently performed on-site PD measurements on an older power transformer, which was transported and installed at another substation for a utility customer. Could you describe the situation and what you wanted to verify for the customer with the PD measurements?
Yeah, we were asked to make some tests on this transformer because before it was transported and also bought by the new utility. And this transformer has a very special design. So the high voltage bushing are not mounted vertically. They are mounted on the sides horizontally. And so normally the transformer should fit in the railway profile to transport it without removing the high voltage bushings. But in this case, the transformer would have been too long for the road transportation. So they had to remove the bushings. And on the new location, they remounted the bushings again, and they had to refill, we call it dome. It's the part where the lower part of the bushing is going into the transformer. And this had to be refilled with a transformer with mineral oil. And so the customer or the operator was not quite sure if there are still air bubbles in this part. And so they asked us to make a PD test. So the PD test was not made before the transportation because we didn't have any indication from the gas in oil analysis.
Thank you very much, Michael. Udo, you and Michael started with electrical PD measurements on the power transformer. Could you describe the test setup used for these PD measurements? How did you go about performing them?
Well, in general, the asset itself defines the actual test setup.
Mm-hmm.
It mainly depends on the voltage rating and the given access points where the high-frequency PD signals can be decoupled.
Mm-hmm.
In this specific case, we're talking about a 220, 2110, and 21 kV transformer. As mentioned by Michael already, according IEC, it is required to measure PD at all terminals rated higher than 72.5 kV during the factory test.
Mm-hmm.
We use the same principle for the on-site testing and decoupled the PD signals on all 220 and 110 kV bushings using C1 of the bushing as coupling capacitor. One MPD800 comes with 2 input channels. So in total, we used 4 MPD800 units to measure at 8 bushings synchronously. The test voltage was induced at a tertiary winding using a diesel generator and a step-up transformer. That's more or less the test setup we used here.
Okay. Udo, in such a substation, there is always surrounding interference or noise. Using the MPD 800 PD measurement system, how were you able to minimize the impact this interference had on measurement results?
Noise signals are often not predictable when performing on-site measurements. The measurement principle of the battery-powered MPD units with its fiber optical communication minimizes the paths where noise can couple into the circuit.
Mm-hmm.
In addition, there are multiple software tools, such as the freely selectable digital filters, or for instance, the three-phase amplitude relation diagram, also known as 3-part, which provides the ability to separate PD sources as well as disturbances such as corona discharge based on the synchronous measuring approach. This feature is very powerful, especially also for online applications.
Mm-hmm.
Getting back to this specific case, we had been, I would say, rather lucky for the offline test, as surrounding connections haven't been energized at the time of the measurement.
Mm-hmm.
The ambient noise level measured within the IEC 60 to 70 frequency recommendation was less than 10 picocoulomb, and this in the middle of the substation. I would say quite impressive. It significantly changed when the transformer was later energized by the grid. Corona discharge was not only measured, but also audible. In this case, the software tool 3-part and a proper filter setting around 2 MHz help to easily separate disturbances from actual PD.
Okay. So, Udo, in performing these electrical PD measurements with the MPD 800 system, you detected a potential problem. What did you discover?
Well, we increased the voltage step by step. There was no PD detected above ambient level around 40 kV. Later, around 90 kV, so 0.7 times nominal voltage, a clear discharge pattern with weighted charge around 1 nanocoulomb was measured. The synchronous measurement and simple overview within the MPD suite software clearly showed that there is something going on at phase U of the high voltage winding.
Mm-hmm.
The phase resolved partial discharge pattern showed high similarities to internal PD. Comparing it with reference data like patterns within SIGRE brochures highlighted that the discharge could be caused by a floating void with interaction at the surface of the insulation material.
Mm-hmm. At what point did you and Michael decide to investigate further by adding an acoustic PD measurement system for defect localization?
In general, I would always recommend to first check the test setup and ensure that the PD-like signals are actually caused within the test object.
Mm-hmm.
After doing so, we used a new MPD 800 tool called the PD event trigger, which allows to display the unfiltered time signal of a freely selectable PD cluster. Comparing the time signal and its frequency spectrum with the calibrator signal injected directly at the bushing tab showed high similarities. In addition, the calibration matrix, which provides an information about the crosstalk of PD activity occurring directly at the bushing, was very comparable to the actual PD crosstalk.
Mm-hmm.
This led to the conclusion that the potential source has to be in a rather short distance from the measurement point. So in an area where an acoustic PD measurement, or rather localization, is easily possible. We use 2 acoustic PD systems with a total of 8 acoustic emission sensors. The sensors were placed in the area of the high voltage exit lead of phase 1U, all the way towards the bushing. The used acoustic measurement system, the PDL650, can perform the measurement in 2 ways. One is the pure acoustic measurement, where one acoustic sensor is used as trigger, and the other approach is an absolute measurement, where an electrical signal measured with the MPD800 provides the start point of the acoustic measurement. Using this approach, one would only require 3 signals to triangulate to the acoustic source location.
So how did you set up the PD localization system, and how was it used in combination with the MPD 800 measurement system already in place?
We expected to measure some acoustic signals in the area of the bushing domes, but that was not the case. Averaging several tens of acoustic signals led to a very clean signal for most of the sensors, pointing towards the area of the winding exit, which is, in this specific case, several meters away from the bushing dome. To confirm the results and even improve the signal quality, we rearranged the sensors. Finally, the area, right where the high voltage exit lead bends down towards the winding, was identified as the spot. It is always a huge benefit if drawings or pictures of the open transformers are available when performing such a measurement.
Thank you, Udo. Michael, after detecting and localizing the defect with the PD measurement systems, what did you and Udo recommend to the customer?
Yes, Scott, we discussed it, of course, with the customer, the situation, and also with the manufacturer, which is very helpful because the manufacturer knows the transformer best. And normally, the next step would be to open the transformer and to look for the reason of PD. But in this case, I mentioned already the special design of the transformer. The whole active part is mounted below the tank cover, so it cannot be separated. And so it's too heavy to lift the active part out at site. And a transportation on the other side to repair shop, this would be alternative, but this was not taken into consideration. You must look that the transformer is 30 years old, and this would be too costly to transport it to the repair shop, make the repair, and transport it back again.
I understand it was decided then to install a temporary PD monitoring system to keep an eye on the situation. Why was this decided, and what is the purpose of using such a PD monitoring system?
The idea is to operate this transformer under controlled condition, even with the partial discharges. And you must look, the transformer is now in service for more than 1 year. And we observe the partial discharge, we check it weekly. And additionally, we have agreed for a limit value for the PD with the customer. And if this limit is exceeded, a warning message is sent to the operator. And then the transformer has to be taken out of service.
I see. And then that would be the point when repairs would be made and such.
Yes.
Okay. Michael, you had mentioned this before. A dissolved gas analysis, or DGA, was performed both before and after the transformer was transported. This is often a first indicator of PD activity, as you mentioned. But could you explain why the DGA performed on this transformer did not indicate what the PD measurement system was able to detect?
Quite sure, but we assume that the partial discharges are located in some solid or in a solid insulation parts. And so they have no direct contact to the oil, and so the gases cannot be produced. But I think I have learned a lesson, Scott.
Yes.
The next time when I will be asked for checking a transformer and to to say if the transformer is okay or not, then I will include also the on-site PD testing, because this case is a little bit special, but you cannot exclude that you have inner parts of discharge which is not shown by the oil or the gases in the oil.
This, of course, was an interesting situation where an older transformer was transported and it needed to be reinstalled for use somewhere else. But would you recommend on-site PD testing literally for all transformers in substations throughout their service life?
I would do it regularly on solid insulation, like cast resin transformers.
Mm-hmm.
And normally it's done when you have an indication by the DGA. But
Okay.
if you, for example, in this case, the transformer was bought as an old transformer by the new utility and at a new location. And in this case, I would strongly recommend to make also a PD test, because the PD test it's an effort, but it can be done in a half day, or let's say in 1 day.
Okay.
And so in this case, I think we should have made it. But I have learned it for the future that we will do it next time.
Very good. So each time you're doing such inspections that you would include that on a regular basis.
Yes, exactly.
Okay. Michael, Udo, thank you both very much for joining me for this episode of Energy Talks, and of course for discussing with me the importance of on-site PD measurements and the various ways of performing them on power transformers.
Thank you very much, Scott, for the invitation. It was a pleasure.
Super.
Thank you, Scott.
Thank you again, both of you, very much. And a big thank you to our audience for listening to this episode of Energy Talks. We welcome your questions and feedback. Simply send us an email to podcast@omicronenergy.com. Omicron has several years of experience in partial discharge testing and monitoring and has the matching solution for your application. Be sure to visit our website for more information at omicronenergy.com. Also, if you are interested in learning more about PD testing and monitoring, Omicron Academy offers you a broad selection of online training courses and webinars. Simply look on our website under training for the next scheduled course or webinar. Please join us to listen to the next episode of Energy Talks. Goodbye for now, everyone.